So far, we have learned what atoms and elements are, how to diagram atoms, how to group atoms together, and predict their properties based on their location on the periodic table. In this video, we will start to learn how and why atoms form chemical bonds. A chemical bond occurs when two atoms bond together to form a new substance with new properties. This new substance cannot be separated by physical means. That means using a filter, a magnet, or distillation will not separate the atoms. For example, hydrogen is an odorless gas at room temperature that reacts with basically every element. Oxygen is also an odorless gas at room temperature that is needed for breathing. But they combine to make water, which is a liquid at room temperature, is non-flammable and is critical for the cells in living things. The water is made of hydrogen and oxygen, but has different properties. We will be using chemical formulas, such as H2O, to show atoms bonding. It is much faster and easier to use symbols than to write out the entire name. Let's take a look at what a covalent bond is. A covalent bond happens between two nonmetals. They will end up sharing their valence electrons to fill their outermost shells and become stable. The atoms can each share one valence electron, which is two total or one pair of shared electrons. This is called a single bond. Each atom could also share two valence electrons, which is four total shared electrons or two pairs. This is called a double bond. We can also discuss triple and quadruple bonds with 3 and 4 pairs of shared electrons. Diatomic bonds are between two atoms of the same element. The bond could also be called polar or nonpolar. To determine if the chemical bond is an ionic bond, a polar covalent bond, or a nonpolar covalent bond, we need to look at the pattern for electronegativity. Electronegativity is basically how strongly an atom pulls on other atoms' electrons. This is really important because we think of atoms as being neutral, but in order to form a chemical bond, the atoms will either transfer or share valence electrons with other atoms and try to fill their outermost shell. This can result in the atom having no charge, a slight charge, or a full charge. We can see from this periodic table that as you go across a period, the electronegativity tends to increase. Not every element follows that pattern, but for the most part they do. As you go up a group, the electronegativity also increases. So the highest number is fluorine, 3.98, and the lowest number is francium, 0.7. We can figure out whether the bond will have no charge, called a nonpolar covalent bond, have a slight charge, called a polar covalent bond, or have a full charge, which is called an ionic bond and is discussed in a different video. To figure out which type of bond will occur, we need to find the difference in electronegativities between the two bonding atoms. If the difference is around 1.5 or higher, then it is classified as an ionic bond. If the difference is about 0 to about 0.2, it's called a nonpolar covalent bond. This means the electrons are equally shared between the two atoms. If the difference is between 0.2 and 1.4, then it's called a polar covalent bond, and the electrons are shared but not equally. Let's try some examples. When carbon bonds with 4 chlorines, we can figure out if it's ionic or covalent. We got to look at the periodic table and get their electronegativities. Chlorine is 3.16, carbon is 2.55. We subtract them, and that is 0.61. That's between 0.2 and 1.4. So this bond would be called a polar covalent bond. That means the edge of the molecule would have a slight positive and a slight negative charge. In the second example, 2 chlorines are bonding together. We would call this a diatomic molecule. Now both chlorines have an electronegativity of 3.16. When you subtract, you get 0. That means that these form a non-polar covalent bond. That means the electrons are shared equally around both. Neither side of the molecule has a slight charge. This next example is potassium bonding with chlorine. Chlorine we know is 3.16, and you can use the periodic table to figure out the electronegativity of potassium, 0.82. The difference is 2.34. That's above 1.5. This is an ionic bond. That means electrons are going to be transferred. This will be covered in a different video. Why don't you try the last 3 examples? Pause the video, determine the difference in electronegativities, and determine if the bond is ionic, a nonpolar covalent bond, or a polar covalent bond. The answers will be shown after you resume the video. I hope you got them all right, but check your work just in case. Now that we can determine if a chemical bond is ionic or covalent, and whether it's polar or nonpolar covalent, we can now look at our first example of a covalent bond. We will start each example by showing the electron-dot diagram. We only need the electron-dot diagram because the valence electrons are the only ones involved in chemical bonds. We don't need to include the protons, neutrons, or inner electrons. We would need to use the pattern for valence electrons to make this easier. Here's the pattern. All elements in group 1 have 1 valence electron. That means 1 electron in the outermost shell. Group 2 has 2, group 13 has 3, group 14 has 4, and so on. We will also need to determine the difference in electronegativity to figure out if the bond is ionic, polar covalent, or nonpolar covalent. Remember, in ionic bonds, the electrons are transferred, while in covalent bonds, electrons are shared either equally or unequally. Ionic bonds are covered in a different video. We'll start by showing the bond between 2 hydrogen atoms. Hydrogen has 1 valence electron. It needs 1 more to fill its outermost shell. When this red hydrogen comes near another hydrogen, represented by the blue hydrogen, they each begin pulling on the other's electron, trying to pull it into its own outermost shell and fill it. Think of it like a tug-of-war match, where the stronger element will pull the electron closer to it. Let's determine which element wins by finding the difference in electronegativities. They're both 2.2, so 2.2 minus 2.2 equals 0. This is a non-polar covalent bond. Think of it like a tug-of-war match where both sides are equally strong. That means the electrons will be equally shared between both. Here is a video animation from the covalent bonds gizmo simulation on explorelearning.com. When each hydrogen shares 1 electron, the pair of shared electrons orbit both hydrogen atoms. We write it using electron-dot diagram where the pair of shared electrons are placed between the 2 atoms. Write the chemical formula as H2. You will often see the single bond between 2 atoms, that's 1 pair or 2 total shared electrons, written like this. When an atom bonds to another atom of the same element, it's called a diatomic molecule, like 2 hydrogens bonding together, for example. This video will be dedicated just to diatomic molecules. There will be a separate video when different elements bond together. Those can form polar covalent bonds. Here is a second example. 2 fluorines bonding together. Each fluorine has 7 valence electrons, and each need 1 more to fill their outermost shell and become stable. Both fluorine atoms are pulling on 1 of the valence electrons from the other fluorine atom. From the periodic table, we can see that both fluorines have the same electronegativity value of 3.98. So the difference is 0. They will form a nonpolar covalent bond. That means, although they are both really strong, neither atom is strong enough to pull the electron from the other atom into its own outermost shell, and 1 electron from each fluorine ends up being shared. Here is a video animation from the covalent bonds gizmo simulation on explorelearning.com. When each fluorine shares 1 electron, the pair, that's 2 total, of shared electrons orbit both fluorine atoms, while the 6 electrons from each fluorine that aren't shared are orbiting each fluorine separately. The atoms have bonded through a covalent bond. The electrons are equally shared, so there is no charge. The molecule is written as F2. You will often see a single bond between 2 atoms, that is 1 pair or 2 total shared electrons, written like this. Here is another example. 2 sulfurs bonding together. Each sulfur has 6 valence electrons, and each need 2 more to fill their outermost shell and become stable. Both sulfur atoms are pulling on 2 of the valence electrons from the other sulfur atom. From the periodic table, we can see that both sulfurs have an electronegativity value of 2.58, so the difference is 0. They will form a nonpolar covalent bond. That means that although the atoms are strong, neither atom is stronger, so neither is strong enough to pull the electrons from the other atom into its own outermost shell, and the 2 electrons from each sulfur will be shared. Here is another animation from the covalent bonds gizmo simulation on explorelearning.com. When each sulfur shares 2 electrons, there are 2 pairs, that's 4 total, of shared electrons orbiting both sulfurs, while the 4 electrons from each sulfur that aren't shared are orbiting each sulfur separately. The atoms have bonded through a covalent bond. We write the molecule using an electron-dot diagram where the 2 pairs of shared electrons are placed between the 2 atoms. The electrons are shared, so there's no charge. You will often see a double bond between 2 atoms, that is 2 pairs or 4 shared electrons, written like this. The molecule is written S2 because there's 2 sulfurs. Here is another example, 2 nitrogens bonding together. Each nitrogen has 5 valence electrons, and each needs 3 more to fill their outermost shell and become stable. Both nitrogen atoms are pulling on 3 of the valence electrons from the other nitrogen atom. From the periodic table, we can see that both nitrogens have an electronegativity value of 3.04. The difference is 0. They will form a nonpolar covalent bond. That means that although the atoms are fairly strong, neither atom is stronger, so neither is strong enough to pull the electrons from the other atom into its own outermost shell, and 3 electrons from each nitrogen will end up being stuck in the middle. We call that being shared. Here is another video animation from the covalent bonds gizmo simulation on explorelearning.com. When each nitrogen shares 3 electrons, there are 3 pairs, that's 6 total shared electrons, orbiting both nitrogen atoms, while the 2 electrons from each nitrogen that aren't shared are orbiting each nitrogen separately. The atoms have bonded through a covalent bond. We write the molecule using an electron-dot diagram where the 3 pairs of shared electrons are placed between the 2 atoms. The electrons are equally shared, so there is no charge. The molecule is written N2 because there are 2 nitrogen atoms. You will often see a triple bond between 2 atoms. That's 3 pairs or 6 total shared electrons written like this. Here's our final example. 2 carbon atoms bonding together. Each carbon has 4 valence electrons, and each need 4 more to fill their outermost shell and become stable. Both carbon atoms are pulling on the 4 valence electrons from the other carbon atom, but both have electronegativity value of 2.55, so the difference is 0. They will form a nonpolar covalent bond. That means that although the atoms are fairly strong, neither atom is stronger, so neither is strong enough to pull the electron from the other atom into its own outermost shell, and 4 valence electrons from each carbon will end up being stuck in the middle. We call that being shared. The atoms have bonded through a covalent bond. We write the molecule using an electron-dot diagram where 4 pairs of shared electrons are placed between the 2 atoms. The electrons are equally shared, so there is no charge. The molecule is written C2 because there are 2 carbon atoms. You will often see a quadruple bond between 2 atoms, that's 4 pair or 8 total shared electrons, written like this.